My name is John Horner, and I'm the Media and Marketing Associate at LARSA Inc. In this tutorial, we'll use LARSA 4D's steel bridge module to create, analyze, and code check a curved steel bridge featuring 4 eye girders. Spaced at 10.6-foot intervals, our girders will be modeled using a single beam element and will be braced by 9 X-type cross frames. Beginning with a skew angle of 30 degrees, our bridge model will have 3 continuous spans at approximately 180, 270, and 260 feet. To begin the tutorial, we'll first set our project units before accessing LARSA's steel bridge module. In LARSA 4D's Input Data menu, select Units, then choose the Imperial Default option and click Apply Conversion to set the current units. We can now open the steel bridge module, which is accessed through LARSA 4D's Design menu. The steel bridge module has a task-based user interface where each task is carried out using a step-by-step procedure, and navigation buttons are used to advance or backtrack through these tasks. The steel bridge module is comprised of 4 main tasks. This includes Step A to generate a new finite element-based bridge model, Step B to create dead load, vehicular live load, construction, and other bridge loading data, Step C to perform AASHTO LRFD code check, and Step D to perform load rating. Following these tasks, the user can create a full 3D finite element model for eye, box, or tub steel plate girder bridges, and then load the model for code-based loading scenarios. To aid design revisions, the user can make structural changes after the model has been created, and then return to Step C and re-perform AASHTO LRFD code check, ensuring that the alterations made are in compliance with the code. When alterations are made, the module automatically scans the project to identify the changes before continuing to perform code check. Before we begin the design process, we'll save our file using the export command located on the top of the module window. For this tutorial, we'll name our file Steel Bridge Example. And notice the module uses a .larst file extension. Using the import command, previously saved LARST files can be opened within the module if further design revisions and code check is needed. With our project now saved, we'll select the tasks we're going to perform within the module's main window. In this tutorial, we're first going to select Step A to generate a new steel girder model, followed by Step B to create our bridge loading data. Once these tasks are completed, we'll review our bridge model in LARSA 4D before returning to the steel bridge module to perform Step C code check. With these tasks checked, we'll hit Next and begin entering the structural information for our model. In the Model Generation task, the module collects the needed structural information in order to generate a 3D finite element representation of the bridge. To begin this task, we'll start by defining the general structure information, including geometry, girder type, section, and material. If we scroll to the bottom of this page, we can see a list of definitions is provided which details the input fields used in this task. The first piece of information to define is whether our bridge girders will be continuous, allowing moments to be transferred from one span to another, or if it will be simply supported, with moment releases automatically created for the girders at pier locations. In this example, we're going to select continuous since we want our moments to be transferred from one span to the next. In the Alignment drop-down menu, we'll see we can choose from Global X or New Bridge Path. Scrolling down to our definitions, we can read that the Global X alignment is used for straight bridge models, while the New Bridge Path is used to create models with curved bridge paths. For this model, we'll select New Bridge Path, which calls on LARSA's bridge path coordinate system to support complex curvature alignments in a simplified modeling environment. In LARSA 4D, bridge paths are defined by establishing a horizontal and a vertical curve. The horizontal curve is composed of one or more straight line, circular, or spiral segments between the control points, which are typically given on site plans with their station and bearing. Once New Bridge Path is selected, the Bridge Path Editor window will open, which is used to input the horizontal and vertical geometry of the reference line for our bridge deck. To define this geometry, we'll start with the horizontal plan curve, which in our model begins with a straight line segment, ending with a circular curve. We'll define the first station at the start of the bridge as 0, and then label its bearing as 70 degrees and 55 minutes southeast, which is the starting location of our bridge alignment. Our next station, which is located at 198.25 feet, will again feature the same heading information of 70 degrees and 55 minutes southeast. The last station to define will be at 730.25 feet and will comprise the end of our bridge model serving as the endpoint for the curve and have a heading of 49 degrees, 24 minutes, and 58 seconds northeast. When entering headings, the user must leave spaces in between degrees, minutes, and seconds, which the program uses to identify the heading's direction. If circular curves are selected, they will automatically fit between the horizontal control points with changes in bearing. Once the stations and headings are defined, make sure that largest arc is the selected curve type within the horizontal geometry curve fitting. While this window is open, I'd also like to note that the Bridge Path Editor features additional tabs which can be used to define vertical elevation curve, bank rotation, and additional spiral options. Should our model have featured a vertical curve, the bottom elevation view window in the editor would update to display the given input. Now that we've entered the alignment information for our curved bridge model, we'll click OK and save the bridge path definition as CL. To continue moving forward, we'll define the abutment and pier locations by clicking Edit Abutment and Piers within the Steel Bridge Modules window. Once the Piers spreadsheet opens, we can enter the location using the station, specify skew, and define the support conditions for each abutment and pier. The first and last entries on this spreadsheet usually represent abutments, while the interior fields are typically used to represent piers. On this spreadsheet, station is the designated x-coordinate of the abutment or pier if the global X alignment option is chosen, or as is the case in our model, the station coordinate uses the station axis of the CL bridge path alignment. In terms of the skew, each defined abutment or pier can have a skew angle, which is entered in degrees. When it comes to degrees of freedom, the support condition at each abutment and pier are entered separately in the 6 directions of translation and rotation. For each direction, you may specify fixed, free, or a spring constant to model the connection to the substructure as a bearing. The first abutment in our model will be simply supported and has a skew angle of 30 degrees. The piers will be supported as rollers, which will fix in all translation Z columns. For the end abutment, they'll be simply supported with fixed supports in translation Y and translation Z. To enter this data, click the first row and set the station as 15, the skew as 30, and rotation X as free. The rest of the default data displayed for this row is correct. For the second row, set the station as 198.25 and the skew as 0. Now set translation X and translation Y as free. For the third row, we'll simply change the station column to 469. In the fourth and last row, set the station as 730.25 and change translation Y to fixed. Once finished, click the button towards the top of the window that reads Back to Main Page, and we'll continue to edit the girders, cross frames, and splice points for our curved and skewed I-girder bridge model. Designed to support I, box, and tub girder steel bridges, LARSA's Steel Bridge module provides flexibility by offering several options in how the program uses finite elements to model steel bridges. For I-girder bridges, you can create your finite element model using a combination of member and shell elements. This option uses beam elements to model flanges, shell elements to model the web of the girder, and rigid beam elements to connect the top flange of the girder to the deck. In doing so, this method allows for easier extraction of lateral bending moments of the flanges. A second option provided by the module uses a single beam element to model the I-girder. In this method, the beam represents both flanges and the web, and the members are defined using the joints at the centroid of the deck with member end offsets. These offsets are used to define the centroid of the beam in reference to the joints located on the deck centroid. Options similar to these are also available to model box and tub girders. For the purpose of this tutorial, we'll model our I-girder bridge with one member for the flanges and the web. LARSA 4D Steel Bridge module includes a variety of steel available in the drop-down list for girders. This list can also be extended by adding custom materials to the module by opening the Input Data menu in LARSA 4D, selecting Properties, and then choosing Materials. For our girder, we'll select steel material A558, which will be assigned to the web, top flange, and bottom flange materials. Once the materials are selected for all three fields, we can go ahead and click Edit Girders. Just like abutment and pier locations, each girder needs to be defined within this spreadsheet. The girder number must start with 1 for the rightmost girder and go up consecutively from right to left. If the girder changes size or has varying transverse location along the bridge, the same girder can be defined using multiple rows. Transverse offset at start and end definitions are used to specify the horizontal or transverse location of each girder relative to the reference alignment of the bridge. The spacing between the top flange of the girder and the bottom of the deck, haunch thickness, can be applied, which includes the weight of the deck but is ignored for stiffness. The columns for web depth, web thickness, top and bottom flange width, along with top and bottom flange thickness, are used to specify the cross-section dimensions of the girder. In the first row of the girder spreadsheet, change the end station to 730.25. both transverse offset columns to -6, haunch thickness to 5.5, web depth to 93, web thickness to 0.625, top flange and bottom flange widths to 24, and lastly, top and bottom flange thickness to 1. Now add a second row to the spreadsheet and change the end station column to match that of the first row. Then change both transverse offset columns to 4.6667. Add another row and change your end station column to match that of the previous row once again. This time, change both transverse offset columns to 15.3333. Add one last row to the spreadsheet and change the end station column to 730.25 once more, and then change the transverse offset columns to 26. In regard to begin station and end station definitions, the station refers to the position along the bridge alignment. For a girder with a transverse offset, the station is measured along the alignment center line first, and the transverse offset is then applied perpendicularly from the alignment center line. Also available in this spreadsheet, the user can put the deck on a transverse grade or cross slope using the vertical offset tab, and additional section dimensions for tub girders can be specified in the tub girder tab. Now that we have our girder information entered, we can click back to main page to close the spreadsheet and return to the modules window. The next part of the design task in LARSA Steel Bridge module is for cross frames, substringers, diaphragms, and lateral bracing for our bridge model. As with abutments, piers, and girders, cross frames and splice points need to be defined if they're going to be featured within our model. The module supports a variety of cross frames including X-type, K-type, and diaphragm types. X-type cross frames can be defined as open or closed. Type 1 and Type 2 K-type cross frames can be used, and diaphragms can be modeled as simple or with flanges. Additionally, a simple internal strut is also available if needed. For girders modeled as single beam elements, diaphragms are modeled as a beam running between the girders. For I-girder bridges modeled with the web as plate elements, diaphragms are modeled as a plate element running between the girders. To begin entering cross-frame information, we'll specify the material, location, and type of the cross frames, diaphragms, and splice points to be used between the girders. Under the cross frames and splice points section of the steel bridge module, change the material from A242 to A588. Now click the Edit Cross Frames and Splice Points button, which will open up the bracing spreadsheet. We'll first notice that the spreadsheet has tab options for type, sections, substringers, and lateral bracings, and we'll make sure that the type tab is selected. Each row in this spreadsheet represents a cross frame, diaphragm, or splice point at a particular location along the bridge. Crossframes are created between all the girders at the specified station, unless otherwise specified, and skew angles can be assigned to each crossframe which use the same system as the skew angle of the abutments and piers. We'll add our first row into the spreadsheet and change the station column to 24 feet, the distance from the bottom of the top flange to 10 inches, and the depth to 73 inches. Now add 8 more rows to the spreadsheet and define their stations as 100 feet, 198.25 feet, 293.625 feet, 393.625 feet, 469 feet, 619.625 feet, 670 feet, and 730.25 feet. With the exception of the first crossframe at 100 feet, which has bays between girders 1 to 3, all of the crossframe stations share the following information: an X-type crossframe which is open, the location of the top of the crossframe is 73 inches as measured from the bottom of the top flange of the girder to the centroid of the top of the struts of the crossframe, a skew angle of 0 degrees, an external diaphragm location, since diaphragms are not used for I-girder bridges, and since the crossframes at stations 100 to 730.25 will be placed between all girders, we'll assign their bay as all. Now we'll change to the Sections tab, in which the cross-section properties of the cross-frame beams and diaphragms are set. Being that our bridge model uses an open X-type girder, only the diagonal bracing section of this spreadsheet will be used. The first thing we'll notice is that the information we entered within the Type tab is already present within the section information. Within the bracing diagonal section, click on the drop-down menu and select New Standard, which opens the Standard Custom Sections Editor window. In this window, we'll click the Bracing Diagonal Section heading and use the above editor to change the girder type from W to L and select the L8 by 8 by 1 option. Then click the check mark to apply the change to all rows within the column. In total, there are 3 options to choose from when setting cross-section properties. Within the steel bridge module, this includes the new standard definition we use to select and import our desired section properties, along with the section option of area only, which enters the cross-sectional area of the cross-frame members, which does not support code check. The third option is to select Section from LARSA 4D's input menu to add the cross-section definitions into the project before opening the steel bridge module. If we use this route, any section properties that are already in the project will be listed in these fields, and code check will only be applied to standard database sections. Even though our training model will not include substringers or lateral bracing, the above tabs can be used to pull up their spreadsheets and enter the appropriate input if these features are required. Now let's click back to main page, and we'll continue with step A by entering the deck information of our bridge model. We'll begin by opening the deck material drop-down menu and selecting Concrete FC4 for the deck material. Next, we'll assign the thickness of the deck, which in our model will be a constant 8 inches throughout the bridge. At this point, we'll make sure the width for the deck overhang is set to 3 feet for both sides. Using these input fields, different overhang widths can be entered for each side of the deck, such as 0, which can be entered to assign no overhang width. Following the right-hand rule, the negative Y side precedes girder 1 and the positive Y side is after the last girder. Meshing is an integral part of the engineering analysis process, which influences the accuracy and speed of the solution. The mesh technology used in the steel bridge module has been specifically designed for steel girder bridges. In this particular type of structure, the refinement of the finite element is controlled by the deck mesh using the deck plate refinement input, in which we'll enter 12 feet for the maximum mesh to refine our 3D finite element model. When working with highly skewed angles or complex bridge alignments, the tolerance of the distance between the node location comes into play when more joints are needed to represent the connectivity of the model. In some cases, joints may be at very small distances apart for an exact representation of the specified bridge geometry, however, this may become too detailed. Joints spaced at a distance less than the node location tolerance, to which we'll enter 1 foot, will be merged. Now that all the required information to generate our bridge model has been entered, you can continue on to the next part of this tutorial, which will create the bridge loading data in step B of the steel bridge module.